ಒಂದು ಮೂರನೇ ದಿನದಿಂದ
ನೋಡ್ತಿದ್ದೀರಾ ಈಗ ಕಂಟಿನ್ಯೂ ಮಾಡ್ಕೊಂತಾರಲ್ಲ ಎಲ್ಲಿದೆ ಇದು Hello? Hello, good morning, students.
Morning, sir.
Good morning. So there is some issue with my laptop. Okay, that's why I just try to use KCS laptop. Okay, right. Hello, Aditya.
Yes, sir. How are you?
Hi, how are you? I'm
good.
fine. How are you?
Yeah, doing good. Long time I haven't seen you.
After a long time. Eh? Right. Then I just heard that you have just been to Bangalore today only, I think.
Yeah, today in the morning actually the flight was delayed a little bit, so I came like 2 hours ago.
Okay. Oh, just 2 hours ago. That's what I just asked Reddy sir. Okay, so let him take some time, let him relax because you traveled all the way from Michigan. Huh? Right? Right.
Yeah,
Right. Fine. Okay. It just we are really happy. It shows the commitment. Okay. It shows the love that you have to the department. Right. Dear students, so we take this opportunity, okay, to welcome Mr. Aditya R. Kumar, okay, who is an alumnus of the Department of Mechanical Engineering, BMSIT, and I am just happy to share that we thought to actually make this program offline. Okay, so we have thought that everything is going to be fine, but because of the delay in the flight, so I'm happy that he could able to join still. With all the travel that he has done from Michigan to Bangalore, and I'm just very happy. Okay, now with I'll just try to give a brief profile of our Aditya. Okay, now Aditya R. Kumar. Okay, he has graduated from the BMS Institute of Technology from the Department of Mechanical Engineering from the year 2007 to 2011. He has graduated in the year 2011. And later on, he has done his Master of Science MS in Mechanical Engineering from University of Missouri from the year 2012 to 2014. So later on, he has worked in many very important portfolios with a good amount of the exposure towards the design skills. So his exposures are in Jaguar and Land Rover offshore development team under the Tata concern, under the TC and the TCS. He has worked there as assistant system engineer for a year and so. And then later on, he has gone with the Beckman Coulter. That is for some few months actually. Okay, so I just missed it. Okay, yeah. 1 second, please. Yeah, right. Then he has worked as a graduate teaching assistant, okay, during his presence there at University of Missouri, okay, and then graduated from University of Missouri, and then he was in the Southwest Airlines, okay, as a flight operation engineering intern, okay, during the September 2014 to December 2014, and then he has worked in as Autofarm engineering GmbH as an application engineer in Michigan, US, and then currently he is working as senior CAD FEA engineer in Magna International. Okay, it's still in Michigan, United States of America. Okay, right. So we are very happy that the Aditya is with us. Okay, with all his the journey, he has come here to give a technical lecture to you. Okay, based on the exposure that he has got, and also the top skills he has acquired is he is good at CATIA, the computer aided design, and Autofarm. Okay, and he is a ASME certified online GD&T examination. Right. Now, basically, as you are also, this is going to helpful for your the career building. So I take this opportunity to welcome Aditya, and I'll wholeheartedly thank you for taking pain in making this to happen. Okay, so thank you, Mr. Aditya, and I request all the students to be alert, okay, during the presentation, and take the benefit of this presentation from our the beloved alumni. Okay, over to Aditya for the proceedings.
Sure. Thank you, sir, for the introduction. And again, nice seeing you all. Thank you for doing this. It's honestly, it's a big privilege coming back as an alumnus and presenting some things. My professional experience after I graduated from BMSIT, something I can share and give back. It's definitely an honor from my side to be here. So friends, I was basically you guys 10 to 11 years ago. 2011 was when I graduated, and I am very aware of what stage you guys are in currently. Maybe some of you have. I mean, it's time we get into the out of the academic world into the real world and see how things work there. Until we are in college, we do a lot of academic certifications. We go through courses. Definitely, it's a building block to get into the professional world. But I would like to share my experience and just open your eyes to some of the things that's available for mechanical engineers specifically, because from the outside, even for you guys who are in the college, I guess you might be a little limited to your opportunities that you will find down the career path. So let's take this seminar as a learning experience. I mean, definitely, even I can learn a lot of things because I'm pretty sure things have changed right now. But let's make this an interactive course. I'll share my experience. I'll exactly go through what I do currently and what my specialization is and how it helps in manufacturing of automobiles. And if you have any questions, please, I don't know what the pattern is, sir, but if they have any questions, they can feel free to ask me those questions. And towards the end of the presentation, I would like to also diverge a little bit and go through career opportunities for mechanical engineers, because there are several career opportunities you can make use of, especially at this time, where the EV markets, which is the electric vehicle markets, are about to boom. So we'll go through that, and hopefully this would be useful for all of you. And towards the end of it, I'll leave my personal contact. So if you have any questions, you can feel free to get in touch with me. I'll be more than happy to share as well. So let me go ahead and share my screen, and let's go through. I'll try to keep it simple in terms of, I don't want to get into too technical. This is just to expose you guys to some of the basically field specializations we have in mechanical engineering. And yeah, we'll start from there. So today's main topic will be application of design and FEA. FEA is the finite element analysis in manufacturing car panels, and I'll be specifically dealing with the outer car panels. So before I get started, so could one of you confirm if you can hear my voice correctly and also see my my first slide?
Yes, sir, it's visible and you're audible.
Okay, perfect. Okay, so as I mentioned, I won't get into like the nitty-gritty details like the formula and everything. And finite element analysis, I have seen that people have mixed opinion about finite element analysis, because I think you guys went through this course last semester in your 6th semester, which happens to be one of the toughest semesters for mechanical engineers. But the applications of finite element analysis in the real world is huge and fantastic. It's not necessarily all formula and everything. I'll just share my experience here. So just a brief introduction of myself. Sir already mentioned some of my portfolio, but just to keep it very academic and professional, I graduated from BMSIT in 2011 with mechanical engineering, and then I already had plans of completing my higher education. So University of Missouri in the US is where I completed my master's degree from 2012 to 14. And then my journey in the field of FEA and design began in 2015. I started as an application engineer at Autoform, and I'll give you an introduction to Autoform as well. And in 2021 July, which is this July, 6 months ago, I started a new position at Magna International as a senior CAD/FEA engineer. Magna International is it's a global supplier for automotive companies. They have their presence in India as well. The branch here is in Pune, and I guess there is a small remote location in Bangalore. I'm not completely sure, but we do. So we do have a global footprint. So the brief agenda, how are car outer panels made? I mean, we know it's basically design, trial and error, and fabrication, manufacturing. We all know all the basic stuff. So let's see like a deeper insight of that. And now, what is the importance of FEA in manufacturing? That's going to be a critical part of today's presentation. And then finally, I would like to also touch base on different career paths within mechanical engineering, right? Okay, so first topic, how are the car outer panels made? So if you just observe a regular car, it doesn't have to be anything specific, just a regular car. What I have colored in red is called, in the manufacturing world, these are called as class A's, right? So class A is anything that's directly visible in a car. Like if you look at a car, these are the things that are directly visible, right? There is a hood, there is the front grille, door, roof. Then these are called as tailgates here. So the department that I work in, it's responsible for design and also the manufacturing of these outer panels. There are about 256 different components, just the sheet metal components. And my expertise right now lies in the outer, just the outer panels. Like when you look at a car, what's directly visible to you? The doors and the hoods. That's what we design and manufacture. So I'm very sure you haven't thought about this, but these are actually sheet metals, like they're steel and aluminum. It really depends which car and which model we are talking, but they are sheet metal and their thickness ranges from 0.6 to 1 millimeter. That's how thin they are. 0.6 to 1 millimeter. That's, you cannot even try to measure it in with your bare hands. We can look at how much an inch would measure. We can look at how much maybe a centimeter would measure. But when you talk about millimeter, it's 1 by 25 of an inch. So that's how small we are talking here. So when we get into such small details, there is a lot of things that come into play. So okay, let me switch to a video to show you how the manufacturing of the car takes place. Right, this is just a manufacturing of the door that you open in a car to get in, right? So let me just walk you through how the door is manufactured. It has a lot of different processes to it. So what happens first is, see the sheet metal that I spoke about. This door that we saw right now, this is what it looks like in its infancy stage. This is the sheet metal. It's only 0.6 millimeter thick. This is the very first stage of that. So this is how the sheet metal, we call this as our coil. This is how it looks. This gets fed into the conveyor line and they get trimmed to the size of the door. Okay. So they get trimmed and then it goes into something called as a stamping press. So these guys come and assemble that on a stamping press. And they're completely flat now, right? The sheet metal is completely flat. It doesn't have any shape. It doesn't have any strains on it. And what these guys are doing currently is they're assembling it on something called as a stamping press. There is a lower punch and there is an upper die. So here there is a lower punch and here there is an upper die. And what happens next is that the upper die comes down at a very tremendous pace. Like this pressure it's applying is about like 200 tons of pressure. That's a lot of pressure we cannot even imagine. When it does that, the sheet metal is initially elastically deformed and then it gets plastically deformed. So we all know as mechanical engineers what happens when anything is plastically deformed, right? When anything is plastically deformed, the shape will stay there. It won't go away. If it is elastic, it will come back to its original position. If it is plastic, the shape will basically remain there. It's very hard to get, it's impossible to get that shape away. So the sheet metal is plastically deformed, and this is what your initial flat metal looks like now. This is your door that is going to be assembled in the car. This is what it looks like because of so much pressure being applied and because of those tools coming down and pressing against each other. That's what happens. That is your door. And then it goes from station to station. It basically trims off the excessive material that's not required. And then, there is something called as a restrike. We won't get into this, but this is the conveyor process, like what happens here. And then the door comes out and the guys will check for surface quality, because surface quality is very, very important, right? When you look at a car, you cannot afford to look at like wrinkles, or you cannot have any fractures in it, or you cannot have any surface defects. It should be very spick and clear, like there cannot be any defects on that. So it's very important, and all these things come into play in the manufacturing process. And then basically they are measured and they are assembled, and we will stop this video right here, but they're assembled after this, and it goes into the assembly line and assembled to the final car. So that's just a brief introduction of how the car is, like the outer panel of the car is manufactured, and this is what happens. So let's go through now, what are the stages of that, right? So now, for example, it can be Tata Motors. They're planning to develop a new car model for 2024, maybe like 3 years from now. So let's go through the stages of what happens now. First stage is the product development. Now, few of you might be having expertise in product development down the line. You might be very good in 3D surfacing using CATIA or NX or SolidWorks. So then you would be looking at a career path of product development, where your job is to basically develop that product, like this hood that you see, what we call as the bonnet in the car. It's your job as a product development engineer to make sure that you develop a product that can be that will be fit in a 2024 car. So the production of a 2024 car has already begun now. That's how early we start in the automotive industry. It's not like there is a 2024 model, we start manufacturing in 2024. It doesn't work that way. We have to start work 3-4 years ago, because there is a lot of things that goes into a car and assembled down the line. So it takes few years to do that. So some of you who can relate to developing new products, new designs, establishing GD&Ts and how those fit in a car, then you can look at a career path of a product developer. It's your job to develop this initial product. So once that initial product, that styling is developed, it's not as simple as it looks, because it has features, it has boundaries, and it has like sharp features here. It really depends on a car. For a SUV, it will be a very big hood. For a sedan, it will be a smaller one. If you talk about a Nano, there was a model, Tata Nano, a few years ago, that was very, very small. So there is a lot of things that go into that. So product developers, here is where your job starts. And then you basically, what you do as product developers is give that product to feasibility engineers, or basically manufacturing engineers. To put it in simple terms, you give that product to manufacturing engineers. Now, it's the job of a manufacturing engineer to make sure that that product is made or manufactured. And this is where my expertise lies. Like, I am a manufacturing engineer, and I get this product from the product development team. Right now, we are getting a lot of electric vehicle projects, because the EVs are definitely on a rise right now. If you think about companies like Tesla, now Rivian, there is a new company, there is Lucid Motors, even Tata is getting into that. So we are getting a lot of projects where we are targeting electric vehicles. now our job begins. So what we do is we take the product that has already been developed, and our job is to make sure that this product is manufactured without any splits or fractures or wrinkles or any surface defects. Now that is something we call in the manufacturing as the advanced feasibility. There is a lot of things that goes into it, but I'll shed some light into what exactly goes into it. So once we get these dimensions and the product models from our product development team, what we do is right now our work is in CATIA. We develop something called as a punch. So we take that product and we basically create surfaces from that product that goes tangentially. I will try to keep this simple, but basically you see the product here. This is the exact same product. And what we do is we develop from its boundary, we try to develop tangential surfaces that goes like tangentially outwards to a certain degree. And that is what in the manufacturing world, the stamping manufacturing world, we call as a punch. So when we go back to that video that I showed you, this punch is what is, let me forward that a little bit. So the punch is what is at the bottom here. The punch is basically the product shape plus some additional surfaces, and it is in the bottom. Okay. And then we create one more surface, just one more surface, which is called as the binder that gets attached to the punch. When the punch gets attached to something called as this binder, we call that as a die. And now go back to that same video. You can see that the die is what is here. It's the cavity. It's a cavity. It's a male cavity. You can see the shape here. It has the cavity shape. So that comes down. The punch from the bottom comes up, and the sheet metal, which is the thin layer, it gets smashed in between. And the metal gains the shape of this cavity here. That is, in very simple terms, that's what is happening. So it's our job to design this upper cavity and to design the lower punch. That is our job. And I put it very simplistically, but it's not as simple, because now comes the role of finite element analysis. You might be thinking, okay, we are done with the design. The design portion is to just create upper cavity and the lower punch, and then you can design your doors. It's not as simple, because now comes the application of finite element analysis. So let's go and see what is the importance of finite element analysis in manufacturing. Let me at this point just pause for maybe 2 or 3 minutes and see if you have any questions. So if you have any questions, please unmute and let me know. We can go through those questions.
So no questions so far, sir.
Okay, good. So I'm assuming either the presentation is going really well or nobody's understanding. Okay, now let's get into finite element analysis in manufacturing. So why is finite element analysis important? Why does finite element hold such a key critical role in manufacturing? Now, when I showed you what happens in this process, I just showed you a very best case scenario where the door is being manufactured without any defects. But because there is so much pressure that is, being exerted by the upper cavity into the lower punch, in the real world, what happens is there is something called a splits. The panel basically splits because it's plastically deformed beyond a certain limit past its ultimate tensile strength. And what happens when the material is basically stretched beyond its ultimate tensile strength? It splits, it fractures. And if you see this, you now will be thinking, okay, what I cannot manufacturing, any car company cannot manufacture cars if the panel is splitting like this. We cannot assemble such panels in a car. So this is where the application of finite element analysis comes in, because just imagine if you design tools, if you design the tools like the die and the punch, and that gets assembled in the manufacturing press, and you begin stamping such parts, your company will file for bankruptcy in about 2 or 3 days, because this cannot happen. So now is where the finite element analysis or the simulation side of things come into play, because before even you can think of machining your tools and assembling it in the press, you have to go back into simulation and validate and analyze if that tool is actually going to work, because these days the simulation softwares are so advanced that you can mimic, you can create your tools in simulation, like just what I showed you in the previous slide here. You can take these tools into simulation and see if the panel that you're making, based on that pressure that is being applied, like 200 tons of pressure, will that panel split or will it come out cleanly? You can validate that in simulation. And that simulation for sheet metal stamping is Autoform, and that's where I worked in my previous job. Autoform is a sheet metal stamping software where you can bring in the tools. Like it could be like 6 months before the production begins. You can bring in those tools into that software and just input your lubrication, your material properties, and the pressure that is being applied. And the software will basically tell you if the panel is manufacturable without problems like splits, wrinkles, and surface defects. So let me go back and show you how the software looks like. So this is what the interface of the software looks like. It's very simple interface, but it is a very, very powerful software. So this is where we import the tools. Like this is a different panel, but this is how you can import the tools. And Autoform, what it does is it has a finite element model, a solver in its behind the graphical user interface. So it will take into consideration the material properties, the pressure, and the lubrication, and it will tell you, see here, it will tell you the part will split here. The part will split. Anything green is safe. Anything red is where you have insufficient stretch. But here there is, if you can look closely, there is a potential split coming up. It means that if you machine your tools and if you assemble that and try to manufacture, the part that you're going to finally manufacture will split or fracture. So what Autoform is telling you is change your design. Go back to CATIA, change your design, probably make the radius bigger, or maybe make the pressure lower here. And by that, you will be able to avoid fracture. That's what this simulation software will tell you well in advance. And the theory behind the working of the software is exactly what you learned in the previous semester. It's just the same. Force is equal to K into displacement. That's all the solver basically bases its capability on. And there is some advanced iterations that it will take place. Yes, it will do some advanced calculations, I agree, but it's not your job as a mechanical engineer to come to into the professional world and memorize formula. Your job is to analyze within the software to see how well these tools can be manufactured. That's your job. So I know you might be overwhelmed with some of the concepts in finite element engineering, but once you get into the real world, this is what you'll be dealing with. You'll be dealing with analyzing fractures, you'll be dealing with analyzing insufficient stretches and all this different nuances. So once we get something once we get a clue like this, it's our job as advanced manufacturing engineers to go back and fix our design. We basically go back to CATIA in this case. I can show you a quick example. We go back to CATIA and say, suppose the part is splitting here. What we'll do as engineers is we'll try to give a bigger radius here so that it doesn't have that sharp edge and the material flows in much more smoothly and the split doesn't happen anymore. So this is how we go back and forth within the software. And once the software tells us that, yes, now the panel is completely makeable or manufacturable without any splits, that's when we machine the tools, and that's when the manufacturing begins, the actual production begins. So there is a lot of process that goes in the background. So if some of you guys now can relate yourselves to being finite element engineers, and if you can relate to that, then this is what you will be having as your profession. This is not exactly the profession, but one of the career paths that you can take is the sheet metal stamping industry, basically the car exteriors. If you're completely into design, then you can think about becoming product developers. But if your expertise is half design and half simulation, like mine, then you are much more suited to become manufacturing engineers, and that has a lot of potential as well. So, in short, I would like to say that once you get into the real world, you're actually working on tools or manufacturing tools. So it's not about theory or not about exams anymore. The actual exams begin in fixing real life problems, and these are some of the scenarios that I have encountered in my job. So for you, looking at your expertise in finite element and design, this is where you can think of having your expertise, well used. So the next thing, so just to summarize the importance of finite element, it saves money upfront. If you machine your tools, let me give you just a very rough estimate of the cost. If you machine your tools for a door panel, the cost of the entire stamping press is about $1 million. So $1 million is $10 lakh. If the part splits, if it doesn't hold good in the manufacturing press, then you're basically wasting $1 million for your customer, which can be General Motors or Tata or Tesla or anything, and then they will right away stop giving you contracts. They won't give you any contracts anymore because you already wasted them so much money. So the entire tool for just one part, I'm just talking about just the door. There are 256 different parts in a car, the sheet metal parts, I mean. And if you just waste, or if you do something wrong within just one part, the tools to manufacture just one component is about $1 million. And if that goes to scrap, then your company is held responsible for that. So instead of doing a design and directly machining and then realizing the problem, finite element analysis will show you upfront if you have a problem, like what I showed in the video here. It will already point out, yes, there is going to be split here. Now you can question this, how accurate is this? This is pretty accurate as long as you get your material properties right. This is very accurate actually. This is just basic finite element analysis. So it will save you money upfront by virtual analysis. It reduces rework in production. In production, there can be problems with the machines because your part is splitting heavily, so your machines don't function properly because the part is splitting. So there could be rework of the machines that can be skipped if you use finite element analysis properly. The third thing is it reduces extra labor, because if your machines don't work, then you need physically some people to go test that machines and see why isn't it working. That's extra labor. So that all leads to optimal design that you can get with finite element analysis. So design and finite element analysis, they pretty much go hand in hand in manufacturing. So now I'm done with what I wanted to present in terms of design and FEA and how that goes in the manufacturing process. I will get into different career paths for mechanical engineers in just a bit, but since it's end of my presentation in terms of my actual concept, let's stop here. And before I proceed with the last topic, which is different career paths, we'll stop here and we'll open the floor for any questions, please. And the questions, they don't have to be in design, in FEA. You are in the 7th semester and you might be thinking about, which company I need to get into, or what kind of work would suit me, or I am still confused what path I should take. So that will come up in a bit. But if you have like any other questions apart from what I showed you, like just looking at the professional side of things, just let me know. That's fine.
Excuse me.
Somebody talking? I heard some voice. I don't know.
Can you hear me?
Yes.
Yeah, so I had a doubt regarding academia prospects of mechanical engineering, like how a mechanical engineer could get into research. So,
Okay.
yeah,
So do you have any specific topic in mind, like any specific specialization in mind?
as of now, no.
Okay.
I just
Yeah. Okay. No.
wanted to know the prospects of it.
Sure. So good question. Are you thinking about like a research assistant in a university, or getting into like being a like a professor, or maybe just getting into research and development?
Yes, something like that.
Okay. So for research and development, there are like right now there are a lot of opportunities, and one example I can give you right now for a friend of mine who's working for Tesla. He was into mechatronics in his like he was very interested in that, and he completed his master's from University of Southern California, and that's where Tesla is actually, like very in that state. And based on his mechatronic experience, and also his keen knowledge in control systems, he tried to he initially got a job in Panasonic, but he got into Tesla because Tesla, it's autonomous. They're getting big into autonomous driving, so they are having there is a lot of potential for mechanical engineers in companies like Tesla, or even like Google, because Google is getting into so much into autonomous driving. Uber, these are all like the big players in the market who are getting into AV and EV, all this stuff. So if you can figure out like the specialization, which definitely like mechatronics, control systems, then the prospect of getting into the autonomous vehicle industry is really good, is what that's my analysis on that.
Understood. Thank you.
Yeah.
So what about other fields in research and development itself, like in material science or similar fields?
Yeah, so material science is one more very important field. Very honestly speaking, if I put material science versus mechatronics or control systems, then I think mechatronics and control systems have a bigger hand, because it's only because the AV and the EV market is picking up so much. But metallurgy and material engineering has its own place. We cannot doubt that, because material, like if you think about it, material science and metallurgy, they are basically the infancy stage of any structure. It can be like any structure you can think of in your car. The material, like how well the material is being processed, how good the properties of the material hold true, and how well the material will behave in production based on its properties. And they are coming up with like materials that we didn't have like 5 years ago. They're coming up with something called as generation 3 materials, which has dual properties. They are coming up with different forms of ultra high strength steels that goes in the underbody of the cars. So there are metallurgy and material science engineers in our company as well, who deal specifically with material properties and development of materials. And it has its own place. Like our company, I can talk about our team. We have two PhD students, former PhD students, who came into our department, and they are our material experts. And we need material experts in every manufacturing field, because material is like the heart of the manufacturing process.
Sir, can you hear me?
Yes.
Yeah. What are the extra skills should I add to my CV so that I can get into a career like you, have a career like you?
So one thing is definitely have good knowledge of design. and be interested. Like I cannot say be a expert in finite element analysis, but be very keen and interested in the field of finite element analysis. That is where my career headed in that direction, because I had a very keen knowledge for finite element analysis, and believe me, finite element analysis, once you get to the real world, it's different from what you studied. Like the concepts are still the same, but how you apply is different. So the skills you would need is understanding of finite element analysis and design. And then down the road, like 1-2 years into your job, you need to be very good at understanding the manufacturing process itself, because everything you design, everything you simulate, end of the day, if you don't know the process correctly, then the design and your analytical theoretical skills will not be very efficient. So 3 things from my side is design, FEA,
Okay.
and understanding of the manufacturing process.
Thank you, sir. And what are all the design softwares that we should be knowing as of now?
As of now, I think,
Basic.
yeah, you guys might be used to SolidWorks by now. So CATIA is, once you if you want to get into automotive, the 2 most used software is Unigraphics, which is UG, and CATIA. It doesn't mean that you need to be expert in both. They both are very similar down the line, but the way they work is a little different. So if a company is hiring you, they will look for either CATIA or Unigraphics. It doesn't mean that if you know CATIA, they will reject you. They'll just say, okay, we use Unigraphics in our company, so you have to get a little adjusted to that. That's also the main software. The most commonly used software, I can say, in professional design world is CATIA.
Thank you, sir.
Yeah. Okay, so very good questions that came up. We'll still have time for questions, but I don't have a slide for this, but the 4 to 5 different fields that I wanted to bring up, and that could be very good career paths for mechanical engineers. And you don't have to force yourself to be in one particular specialization. Like if you are passionate about mechanical engineering, you have very different options. So first thing is materials and metallurgy. That is one field you can get into, which is it has its own benefit. Lot of people do their advanced degrees in materials and material science and metallurgy. As I mentioned, it's like the heart of your manufacturing process. So everything, like any component that is being manufactured in a car, just barring the dash panels, maybe they have to go through some of the other kind of material, apart from even plastic. That's kind of a material, end of the day. So material science and metallurgy is one thing you can choose down the line, especially if you're getting into higher studies like master's degree. Many people opt for that. Second thing is design, just specifically design. As I mentioned, product engineers, people who can think out of the box in terms of design. How should my next car door look like, or how should the next car look like? A lot of things go into the action planning and eventually coming up with the design for that. So that is specifically design in mechanical engineering is something you can look at. That is one more field. Third field is very specifically finite element analysis. Again, it has a very huge, I should say, vast scope in the manufacturing world. So finite element analysis, many companies look for FEA engineers. Something you might want to keep your eye out for, and the demand is pretty good for FEA engineers as well, because FEA, the scope of FEA, I can tell you, is in like crash testing of cars, where they take the prototype model of a car and they go into the tunnel and just crash it, because they would like to see eventually how the car will perform in an accident. Like, nobody would like to get into an accident, but if your car is in an accident, they would like to see how it functions. Will the passengers be safe? Will the airbag deploy? Which structure in that part in that car will crumble first? Will the car topple and roll over? And what will happen to the people inside? They will create the dummies of human beings, and they place it inside the car and do the crash testing to see how it affects that dummy models. So finite element analysis comes into play in a lot of field, like crash testing, topple testing, tunnel testing, many other things. So that is something you if you are interested, it's very exciting. End of the day. Fourth thing is fluid dynamics. You already, I think you still have courses on fluid dynamics. You already had courses on fluid dynamics. That's something you can think about. It has its own applications. People look out for fluid dynamics engineers in the real world. Has a lot of applications. I can't remember like the company on the top of my head, but definitely there is a good scope for that. Fourth one I can think of is heat transfer. Like we talk about heat transfers. You might have had. I'm not sure if the 6th semester ANSYS lab. Yeah, I think it deals with heat transfer as well. They require engineers in engines and propulsion and transmissions. They require some heat transfers experts there, because a lot of things go into it. How does one particular underbody structure perform under a specific heat? And it also, if you look out of the automotive industry, in oil and gas industries, in construction industries, the heat transfer experts in mechanical engineering, they are very sought after. So these 4 fields, you can, I think it was 5 I mentioned, sorry, 5 fields. And the 6th one, I'll combine this, but right now they're picking up a lot of pace. This one particular field I already mentioned, it's mechatronics and control system engineers. And you don't have to be, electronics, electrical background. You can still be mechanical engineers and get into control systems and mechatronics. And we have, I think, both our professors here, they teach those subjects, and they're very, they're beautiful subjects actually. And how they are going to pick up pace in the professional world in the next 5 to 6 years, you will be surprised to see our EV automotive industry, how it will pick up pace in this decade. Because in the US especially, there are certain states that have already committed to going completely EV, like no more IC engine vehicles anymore. They have completely committed to going into the EV route in 10 years. So the control systems and mechatronics engineers, if you have a passion for that, or if you don't have a passion yet, but you're looking for a field, I am not a control systems or mechatronics engineers, but I would recommend keep an eye out for that. I mean, explore your options there to see if you can, gain a specific interest in that topic. So, and again, very honestly speaking, once when I was in your position 10 years ago, I wasn't sure. Like, I knew that I will be in mechanical engineering. I don't want to get into something else. But at the same time, I wasn't completely sure what specialization I should look out for. And like 10 years ago, if that time EV and the AV markets weren't even started, but if I was at your position at this time, and if somebody like me was giving a speech and told that keep an eye out, then yeah, maybe I would have looked out and see, made some research to see if what are the benefits and what is the scope for this field. So definitely keep an very close eye out for that, to see if it could be higher studies, or if it could be getting into companies that employ mechatronics or control system engineers. But they will be having very good demand in the next 6 to 10 years. That's what I can say from my experience. So that with that, that's pretty much what I had for today. That wraps up the full presentation. And again, I would like to thank our professors for conducting this. As I mentioned, I couldn't be there in person, but I just reached Bangalore 2 hours ago. But at the same time, even though the journey was stressful, I wanted to be here because it's one way of giving back to the college and also the professors who work so hard to educate us and also guide us in the right way. So hopefully you guys, I wish and I hope all of you have a very successful career ahead of you, and down the line, please, I would say, stay humble and don't forget your roots, and just go back and thank people who have helped you in your career. Right now, it may not you may not make complete sense of it, but definitely down the line you will see this as an opportunity to give back. And I'm very glad that I'm in that position now. But at the same time, thanks to our professors for for all the help and also for the organization.
Thank you, sir, for the session.
Thank you.
Yes, you're welcome. Good luck. Okay, sir, can we end the call, or do we have anything else? I think we can end the call. All right, again, good luck everybody, and have a good day for today. If you have any questions, you can definitely get my contact from KCR Reddy sir. I'll be more than happy to assist in the future. But for now, thank you again, and all the very, very best for your future, and specifically for the next semester. All right. Thanks, friends, and good luck. Bye.
Thank you.